the last lecture, we established the framework of the Rayleigh-Schrödinger perturbation theory. In other words, stationary perturbation theory. The perturbing Hamiltonian was independent of time, and just to get the notation straight, let's look at some of the notation that we used yesterday. So the Hamiltonian had the unperturbed part h naught and lambda h prime, which was the perturbation. And then of course the original unperturbed Hamiltonian had a discrete set of eigenstates psi n0, the corresponding eigenvalues being given by En0. Because of the perturbation, both the energy and the wave functions changed. However, the new wave functions could still be expanded in terms of the old basis set psi n0, and the new wave functions could well be written as the old one plus the effect of the perturbation. So to first order, it would be lambda psi n1, then lambda squared psi n2 plus. Correspondingly, the new value of the energy would be the old unperturbed value, plus to first order in lambda you had En1, then the contribution to second order was En2, and so on. So this is what we had, and we also established two interesting and important results, namely an expression for psi n1 and an expression for En1. In fact, we had an expression for En(s), where s could be 1, 2, 3, anything. So basically we had the result that En1, that is the energy because of the perturbation, the extra energy contribution, is simply the expectation value of h prime in the unperturbed basis psi n0. Further, the first order wave function, the contribution psi n1, is summation over p not equal to n psi p0 h prime psi n0, and of course there is a state there psi p0 divided by En0 minus Ep0. It's pretty clear that we are looking at the non-degenerate case, because if indeed there is a degeneracy, there is going to be a problem here, because if n is equal to p, there is a problem in the denominator, and the formalism has to be adapted suitably if we discuss degenerate perturbation theory. But right now we are looking at the non-degenerate case. So that's what we are doing. We use this to find out the first order contribution, En1 and ket psi n1 in the case of the linear harmonic oscillator, to which there was a perturbation added. So in the case of the linear harmonic oscillator example, we had h naught, which was p squared by 2m plus half k x squared. So k is m omega squared, and h prime was simply b by 2 x squared. So we had set lambda equals 1 and this was also of the form constant times x squared, and therefore the harmonic nature was not destroyed. So this is the simplest example we can think of. And today we look at something else. We look at an anharmonic oscillator. So basically, therefore, the perturbing term would not be quadratic in x. So let us consider the case of the anharmonic oscillator. As an example. So again I set lambda equals 1, that is just for bookkeeping, and h prime, let us say, is d x to the 4, d is a constant. So what do I have here? I do not want to battle with an x cubed term. If you just plotted potential v of x is equal to x cubed versus x, find that there is no lower bound. So I take a safe case, I take h prime as dx to the 4. And now our aim is to find out what is En1 and psi n1. So we just have to plug in values into that expression that we had. So En1 is simply psi n0, h prime psi n0. Since we are discussing the oscillator Fock basis, in my notation this is ket n, and of course there is a d x to the 4 ket n. Because you can do one of two things. You can write the wave function, the state in the position representation, put in the Hermite polynomials, do an integration and get hold of this expression. But for the moment I would prefer to put in x in terms of a and a dagger, the ladder operators, and then I just have recall that x is root of h cross by m omega 1 by root 2 a plus a dagger. So let us put that in here. So En1 is d h cross by m omega whole squared, because there is an x to the 4 and there is a 4 also out here. So those are the overall constants that I pick up, and then I have the expectation value of a plus a dagger to the power of 4. So let me just write it in this fashion. So this is the contribution. Of course I know that a plus a dagger the whole squared can be written as a squared plus a dagger squared plus 2 a dagger a plus 1. So I put that in there, and I just have En1 is d by 4. I'd like to write this as h cross omega by k the whole squared, because remember that m omega is just k by omega. So that's what I put on there. And then I have n a squared plus a dagger squared plus 2 a dagger a plus 1 times the same thing, a squared plus a dagger squared plus 2 a dagger a plus 1, and a ket n out there. The point that I am trying to make is this. Out here a squared acting on n would lower it to the state n minus 2, and therefore I need to have a term here. I need to use only those operators here which will bring the state n minus 2 back to ket n, because finally I need to take the inner product of ket n with that state. So the only contributing terms because of the orthonormality of the states, are n a squared a dagger squared ket n, n a dagger squared a squared ket n, of course n a dagger a ket n, and then of course just ket n 1 ket n. These are the only terms that can contribute, because as you can see, if the power of a dagger is different from the power of a, there is going to be a mismatch, and the inner product of ket n with this state is going to be 0. So let us substitute that in and see what we get. So En1, which is the first order contribution, is d by 4 h cross omega by k the whole squared n a squared a dagger squared n plus n a dagger squared a squared n plus 4 expectation value of a dagger a dagger a. Then I also have a contribution from 2 a dagger a here and 1 there, and similarly from 2 a dagger a and 1 here, the product. Therefore, I have a 4 n a dagger a n, and then of course I have a 1, that was the last term. There was a bra n, there was a ket n, there was a 1 out here. So this is what I am going to have. This object a dagger squared on ket n gives me a root of n plus 1 times root of n plus 2 ket n plus 2, and a on ket n plus 2 gives me first an n plus 2, and then it gives me an n plus 1. So that is all that I get here. Similarly from here I have root n minus 1, and when a dagger acts on ket n minus 2, it just increases it to n minus 1 and n. So that is the contribution from the second term. Now I would like to combine these two terms and write this as 4n a dagger a times a dagger a plus 1 n plus 1. And this is clear, this is simply going to be n times n plus 1. And therefore, this object just becomes h cross omega by k whole squared, n plus 2 times n plus 1, that is from the first term, and then an n minus 1 times n from this, and then a 4n times n plus 1 plus 1. So let us see, this simplifies out apart from these overall constants. I have an n squared here and an n squared there, that is a 2n squared plus a 4n squared. So I am just going to replace the n squared terms by 6n squared, and then that is a 2n plus an n, that is a 3n, minus an n here which is a 2n, but then there is a 4n there, so that gives me a 6n. And as to the constants, I have a 2 here and a 1 there, so that is a 3. So this is what I have. Of course, I can make this look better, and I can pull out a 3 and do things. So essentially you can simplify this, but this is what you have. H cross omega by k squared d by 4, 6n squared plus 6n plus 3. So this is the contribution from the anharmonic perturbation. And therefore, in this case, the total energy is simply going to be to first order. In first order perturbation theory, the energy is n plus half h cross omega, which is En0, and then there is this extra contribution which we have just now figured out, and that is En1. This is the case of the anharmonic oscillator, where we are doing time independent first order perturbation theory. So, now let us look at the wave function itself. So, psi n1 in this case is summation over p not equal to n. Psi p 0 h prime psi n 0, that matrix element ket psi p 0, and the denominator has an En 0 minus Ep 0. This is what we showed as a general expression, and now we need to substitute for h prime. So, that is the same as dx to the 4. So, that is the same as saying that psi n1 is summation p not equal to n, p x to the 4 n by En 0 minus Ep 0, and we know that that is just n minus p, because this is an n plus half h cross omega, and that is a p plus half h cross omega. So, I just get an n minus p ket p. Once more I have to substitute for x to the 4. So, apart from constants, I am not going to mention those here, I would essentially have the following: 1 by n minus p, there is of course a ket p, and then I have p a squared plus a dagger squared plus a dagger a 2 a dagger a plus 1 times a squared plus a dagger squared plus 2 a dagger a plus 1 ket n. And this is what I need to simplify. Clearly, there will be a Kronecker delta coming from this, and that is going to change the value of p. Now, if you look at this, this is going to contribute terms corresponding to ket n minus 2, ket n plus 2, and ket n. This object here, bra p a squared plus a dagger squared plus 2 a dagger a plus 1, is merely the Hermitian conjugate of that, except that I have replaced n with p, and therefore, the contribution here gives me terms p minus 2, ket p minus 2, ket p plus 2, and ket p. That is what I get out of this. You have to look out for a situation where p is not equal to n, and therefore, you cannot, for instance, have a contribution delta p n. Such a term will not contribute to this. Now, what would contribute would be delta p minus 2 comma n, the Kronecker delta p minus 2 comma n, delta p plus 2 comma n, p comma n minus 2, and p comma n plus 2. So, essentially the contribution would be from the following: the first order contribution to the wave function would clearly have the summation, and then there is a term which has delta p n plus 2. I am not putting down these things explicitly, and then another which has delta p n minus 2, and then of course delta p minus 2 with n plus 2, and a fourth term which is delta p plus 2 n minus 2. So this is what I have, and therefore what are the states that contribute in this order? Again, without putting in all the coefficients, once I use the Kronecker delta and remove the summation, I will have a term which has n plus 4, another which has n minus 4, and then of course n plus 2 and n minus 2. You could say psi n plus 4, psi n minus 4, psi n plus 2 and psi n minus 2, but I have just used this notation. So essentially the perturbation has done the following thing. The state which was originally ket n has now become to first order psi n 0 plus psi n 1. This was the original state, and this is what I have to first order, and this involves other states. It involves psi n plus 4, psi n minus 4, psi n plus 2 and psi n minus 2. The perturbation has done this. However, the system still continues to have a discrete spectrum. I am able to expand the perturbed wave function in terms of the original basis, and then when I go to second order, there will be a different combination of states that will contribute in the second order. The second order contribution, we can calculate it using a similar program as I did in the first order, just a wee bit more messy perhaps, but we will attempt to do that. Now that we have the contribution En1 and the wave function psi n1 from the first order perturbation theory, we have to use those as well as the zeroth order values En0 and ket psi n0, feed that in to get the second order expressions. So in second order perturbation theory, you want to look out for coefficients of lambda squared. Inputs are En0, psi n0, En1 and psi n1, which we have computed from the first order calculation. And the aim is to find the second order contribution En2 and the corresponding contribution, perturbation contribution to the wave function, that is psi n2. In order to get the expressions for En2, En2 is something we already know because we already have a general expression. En(s) is psi n0 h prime psi n s minus 1, and indeed that is what helps, because in order to find out the contribution to a certain order, you need to know the wave function only to a lesser order. So this anyway was the general expression for the s order contribution to the energy, but now we need to get an expression, and therefore in our particular case En2 is psi n0 h prime psi n1. So the input is psi n1 in order to get En2. So that is the same as psi n0 h prime. So psi n1 itself came as a summation. It was a summation p not equal to n. Psi p 0 h prime psi n 0 times ket psi p 0 and there was a denominator En0 minus Ep0. So, this is En2. So, let us write this better. So, it tells me that En2 is summation p not equal to n. I already have the matrix element psi p0 h prime psi n0. That was already here, and I have another matrix element psi n0 h prime psi p0. And then I have this denominator En0 minus Ep0. And therefore, this can be written as summation p not equal to n h prime p n h prime n p. So, I could well write this as h prime p n squared by En0 minus Ep0. So, this is clearly the expression for En2. But now let us look at the wave function. How do we get an expression for ket psi n2? We repeat the algebra that we did yesterday. Start off with the eigenvalue equation h naught plus lambda h prime acting on psi n0 plus lambda psi n1 plus lambda squared psi n2, which is what we are out to find, plus so on, is En0 plus lambda En1 plus lambda squared En2, and we have already got these values, times psi n0 plus lambda psi n1. So, we write out the series like this. That is what you have. So, you need to look out for terms involving lambda squared. That is what you mean by second order perturbation. So, I get a contribution h naught psi n2 from there, plus lambda h prime lambda psi n1, so plus h prime psi n1, and that is all that I have from the left hand side of this equation. Now, this object is equal to look at this En0 psi n2 there is a lambda En1 and a lambda psi n1 there. So, plus En1 psi n1, and then of course, there is an En2 psi n0. By now, it is clear how a general say nth order perturbation theory or kth order perturbation theory is going to be. It is going to involve states at this level. It uses both h naught and h prime, and it involves all states psi n k down to psi n0, and similarly it involves all the energy contributions up to E n k and wave functions up to psi n k. So, one can easily guess the general pattern and write that down, but for the moment we are interested in second order perturbation theory. So, what we can do is the following. Suppose you choose k not equal to n, and then you find out psi k 0 h naught psi n 2 plus, perhaps we can group the factors before that. Let me take the psi n 2's to one side. So, I have h naught minus E n 0 psi n 2 plus h prime minus E n 1 psi n 1 equals E n 2 psi n 0. Makes things more convenient because now I will choose k not equal to n and try to find various matrix elements. This is essentially the procedure that we followed even when we did first order perturbation theory, except that we are going to repeat it here, and therefore I have choose k not equal to n, and I have psi k 0 h naught psi n 2, that is the first term, minus E n 0 psi k 0 psi n 2, this inner product. So, that is what I get from the first term. Then from here I have plus psi k 0 h prime psi n 1 now. I will put in the expression for psi n 1 later when I simplify, minus E n 1, that is a number, psi k 0 psi n 1. Out here on the right hand side, this is a number E n 2, but then I have the inner product psi k 0 psi n 0, and we have selected k not equal to n, and therefore this object is 0. I also use the fact that h naught psi k 0 is E k 0 psi k 0, because remember that the psi k's are the eigenstates of the unperturbed Hamiltonian, psi k 0's are the unperturbed Hamiltonian eigenstates, and then once I use that, this expression simply becomes E k 0 minus E n 0 psi k 0 psi n 2 that is what I get from these two terms. That is equal to E n 1 psi k 0 psi n 1 minus psi k 0 h prime psi n 1. As I did yesterday, I can simply bring down the E k 0 minus E n 0 to the denominator on the right hand side, and that gives us the following. So, I now have an expression for the overlap of psi k 0 with psi n 2 and that is just E n 1 psi k 0 psi n 1 that is the first term minus the matrix element psi k 0 h prime psi n 1 divided by E k 0 minus E n 0. Remember that k is not equal to n. So, this is what I have. So, all we need to do is do a summation over k not equal to n psi k 0 with both the left hand side and the right hand side of that expression. En1 summation over k not equal to n psi k0 psi k0, that is the first term, psi n1 minus psi k0 psi k0. So I can write this better. So I can just write this as En1 psi k0 psi n1 times psi k0, that object that I have introduced there. That is my first term. Similarly, the second term is psi k0 h prime psi n1 times psi k0. So this is what I have in the numerator, and the denominator is an ek0 minus en0. What do I have here? We know this, and I am merely emphasizing what I said in the last lecture. This is the completeness of states, but now you are choosing k not equal to n, and therefore this object is 1 minus psi n0 psi n0. If you substitute this out here for summation over k not equal to n psi k0 psi k0, the first term is simply psi n2, so let us put that in. That is because of the identity. The second term has the inner product of psi n0 with psi n2. And remember that psi n2 is part of delta psi n. It is the second order contribution to the perturbed wave function. And therefore, we started off by saying, the formalism started off by saying that delta psi n has no contributions along the direction psi n0, and therefore that inner product is 0, and all I have here is psi n2. This was precisely the manner in which we went about doing first order theory as well. And therefore, on the left hand side I have psi n2, ket psi n2, for which I am trying to find an expression, and then on the right hand side I have this object. I have two terms here. I should substitute for En1. En1 is simply the matrix element psi n0 h prime psi n0, and therefore I would like to call this h prime n n, the nth matrix element of h prime. Now if I look at psi n1, for that too I need to make a substitution, which I will. I recall that psi n1 is summation p not equal to n psi p0 h prime psi n0 times ket psi p0, and then there was a denominator which was en0 minus ep0. So we have to put in as inputs this expression for En1. I can always call that h prime nn, and then I have an h prime pn psi p0 by en0 minus ep0, which comes both here and there instead of psi n1. So let us put that in, and that should more or less complete the exercise. The expression for psi n2, which is the second order contribution in the perturbation to the wave function, is simply made up of two parts. The first one is summation k not equal to n h prime n n, that comes from there. There is an ek0 minus en0 in the denominator, which we will keep. And then there was an inner product of psi k0 with psi n1, and for psi n1 I have the following object. I have H prime P n, but there is a summation P not equal to n. So let me write summation P not equal to n. H prime P n, which is a matrix element. And then of course I have a psi p 0 out here, which I put there, but that is not all. I also have a psi k 0. That is my first term. And then there is a second term that comes with a negative sign. There was a summation k not equal to n anyway. There is a psi k 0 h prime, but then I substitute for psi n 1 again. The fact that p is not equal to n and k is not equal to n does not prevent k from being equal to p. And therefore, here I have a psi n 1 and psi n 1 is h prime p n psi p 0. I have a denominator ek0 minus en0, which was always there, but here I should have also introduced an en0 minus ep0 when I expanded for psi n1. So here too there is an en0 minus ep0. This was already there, and this came because I wrote out an expression for psi n1, but of course the matter does not stop here. Remember that there is a ket psi k 0. So this is what I have for psi n2. Needless to say that this gives me a delta kp and therefore one of the summations goes away. Such a thing does not happen in this term, and I have to retain both the summations. So this is what I have finally. After using the Kronecker delta and getting rid of one summation, the first term is put out here, and the second term is what I have here. I have put that first and then put the first term in. The point is this, that since n is not equal to p and n is not equal to k, the problem of a denominator that blows up does not arise. Clearly, if we were dealing with degeneracies, then something has to be done to take care of a situation where say en0 is equal to ep0 if there is a degeneracy problem. We will discuss the degeneracy situation later, but as it stands, the message is this, that you do a perturbative expansion. In this sense, you expand in powers of lambda. You could stop at first order, second order, third, depending on how much successive terms contribute. You could decide whether the series can be truncated or not. Now, if you were working with a problem where the higher order terms contribute significantly, then clearly the perturbative approach is not going to help. Typically, that is what happens most of the time when you deal with strong interactions, nuclear forces. On the other hand, perturbation is a very useful technique when we do problems involving electromagnetic interactions, and because the electromagnetic coupling constant in terms of which you do the perturbative expansion is given by E squared by h cross c. So, your lambda in that case is E squared by h cross c, and that is small, that is 1 by 137, and therefore, subsequent terms could in principle be smaller. Therefore, the only other wrinkle to this problem is the degenerate situation, as I said, and we will take that up a little later.